We're extremely delighted for our next speaker, which is Professor Ellen Mosley-Thompson from the Department of Geography at Ohio State University, and also a senior scientist at the Bird Polar Research Center. Ellen was educated at Marshall University for her bachelor's and got her PhD and master's at Ohio State.
Atmosphere for 70 to 120 years. This is definitely should give us a little pause. We should think about this. The other fact is that the decay of fossil fuel CO2 in the atmosphere has this long tail, such that 33% of the emissions today will still be in the atmosphere 100 years from now, and 1,000 years from now, 19% of the emissions will still be with us. This is an issue that will take a long time to resolve. Now, as Peter was reading the introduction, he mentioned our team. And for 30 years, the team at Ohio State that Lonnie and I put together have drilled ice cores around the world. This map shows all of the places from which we have extracted ice cores. We've had a presence in the polar regions, in Greenland, in Antarctica. But one thing that distinguishes our team is the fact that we drill ice cores on the tops of the world's highest mountains in Tibet, up and down the axis of the Andes in Alaska, the Russian Arctic, Kilimanjaro, and in New Guinea. One of the reasons for this is there's no single best ice core. There's no single best place to go to drill an ice core, because where you go to drill an ice core depends upon what the question you are asking is. And when we are interested in global scale phenomena, then we need to have a spatial distribution of ice core records, because ice cores intrinsically carry with them a local to regional signature. So here we can see an example of this. Let's start with the lower panel. This is a composite oxygen isotopic history from these three ice cores in the South American Andes. This is today, going back 2,000 years. The oxygen isotope is shown here as z-scores around the mean. In other words, these are deviations. Up is warm, down is cool. You see a nice signature of the Little Ice Age cool period. You see a modest medieval warm period, or warm anomaly, as it's often called, in the South American record. But here is the composite from 4 ice cores from the Tibetan Plateau. And you see no Little Ice Age and no medieval warm anomaly. Now, this isn't surprising in terms of the South American Andes that we see the Little Ice Age in the medieval warm period, because the source for the moisture for these glaciers in the Andes is actually the Atlantic. And it's well known that around particularly the North Atlantic Basin, we have a very strong signature of Little Ice Age cool period and the medieval warm period. Now, if we take those records and composite them, we have now what we call the tropical ice core composite. And the one feature that stands out most strongly is the isotopic enrichment of the 20th century. And then when we plot our tropical composite with the Northern Hemisphere reconstruction shown in blue, and it's important to note that that reconstruction is based upon many tree ring series, some coral records, some high-resolution lake sediments, and ice cores. And then in red we have the meteorological observations. And you'd have to conclude that over that 2,000-year history, the tropical records composited don't look significantly different from the Northern Hemisphere reconstruction. But both, again, carry the signature of the 20th century warming, and particularly the stronger warming in the latter 50 years. Now, ice cores